Hello everyone, and welcome to the continuation of the proof to the transmission line equations. Right, so in my first video I said that if I apply a certain voltage V over here and there's a current I over here, and we take a very small section of L, R, and the rest of the primary constant, the current here, or the current at the output, should be I plus delta I, and the voltage at the output here should also be V plus a certain delta V, in the sense that if I apply 10 volts at the input, the voltage at the output should be less than 10. It shouldn't be more than 10, or else we've violated the law of conservation of energy, right? So at the end, we proved that voltage in terms of space and time was equal to V plus E minus gamma X plus V minus E positive gamma X. And we continue to say that delta V was equal to negative R delta X plus L delta X multiplying I, because the voltage drop was across these arms, this L and this R. So we said that delta V was R delta X plus the impedance of L was J omega L. We had I over here. So delta V, as we went on, we said that we had delta X to be common, so we brought it out. So it was like this, and we had I. So to be able to get rid of the transient time effect, we took the limit as delta X approaches 0. Delta V over delta X. So we took the limit as delta X goes to 0, and we had minus R plus J omega L I, and eventually we had dV over dx is equal to minus R plus J omega L I. So we had this equation in terms of the voltage, and we proved that the voltage was this equation up here. So if you want to use in terms of current, we can see that I, or the current in terms of space and time, will also be I plus E minus gamma X plus I minus E positive gamma X. So what we have to do now is to find what I is. So, and we know that from this equation we can find I. We can say that I will be equal to dV over dx all over minus R plus J omega L, which is the same as 1 over R plus J omega L multiplying dV dx over here. So we can say that I will be equal to minus 1 over R plus J omega L times, we have dV over here, but let's look at something. dV, this V, we have V over here, and V was this, so we input V plus E minus omega X plus V negative E omega X, like this. Right, so let's continue. So now our equation is I, which is equal to minus 1 over R plus J omega L times d dx. Here was the V, but we had V to be V plus E minus omega X plus V minus E positive omega X over here. So if we continue, we will see that I will be equal to minus 1 over R plus J omega L times, if we differentiate this, right, if we differentiate this, we are going to have minus gamma V plus E raised to the power minus gamma X plus positive gamma V minus E positive gamma X, right? So if we simplify this, we have minus gamma, gamma is common here. So if we take minus gamma out, we are going to have minus 1 over R plus J omega L. By taking minus gamma out, minus gamma is going to multiply this minus 1 over here. So we have in this bracket v plus e minus gamma x. But take note, since you took minus gamma out, here is going to be negative, right? V minus e positive gamma x. So we will see that we will have minus 1 times minus gamma. We are going to have gamma all over r plus j omega l multiplying v plus e minus gamma x minus v minus e positive gamma x. But we remember that we proved that gamma was equal to root r plus j omega l multiplying g plus j omega c in my last video. So knowing this, we can substitute this into this equation. So I'll have I to be equal to root of r plus j omega l multiplying g plus j omega c, that is for this gamma, all over r plus j omega l, and I'll multiply this by v plus e minus gamma x minus v minus e positive gamma x. And from here we know that r plus j omega l will cancel out 1 over here, so we're going to have g plus j omega c all over r plus j omega l by doing the math times v plus e minus gamma x minus v minus e positive gamma x. So let's say this is equation 1. By comparing this equation 1 with 1 over z naught times v plus e minus gamma x minus v minus e positive gamma x, let's say this is equation 2. Comparing these two equations, we can see that 1 over z naught is equal to root of g plus j omega c all over r plus j omega l. But then if we want z naught, which is the characteristic impedance, we will see that we will have r plus j omega l all over g plus j omega c. And this characteristic impedance is a very important parameter in microwave. So from equation 2, if we multiply this through by this, we are going to have v plus e minus gamma x all over z naught minus v minus e positive gamma x all over z naught. Why? Because we know that v is equal to Iz. So from this, we can write this equation. So for the current, in terms of transmission line equations, you can write it as this. So what if we take into consideration our transmission line being lossless? This means that in the ideal case, the transmission line has no losses or no attenuations. So if you remember, we concluded that gamma was equal to alpha plus j beta, and this alpha was the attenuation constant, and this b was the phase constant. Right, so if we are saying that our transmission line is lossless, that means there is no attenuation. Therefore, the attenuation constant here is 0, meaning that at lossless transmission line, or for a lossless transmission line, propagation constant will just be equal to j beta. Let's say this is equation 1. But if we remember, we also proved that, or we concluded that propagation constant was also equal to root of r plus j omega l multiplying g plus j omega c. Again, if you are saying that a transmission line is lossless, that means the real part of this equation is 0. That means r and g are all equal to 0. So it means that our propagation constant will be equal to, since r and g is 0, it will be left with just j omega l multiplying j omega c, which is the same as we're going to have j squared, omega squared, and lc. So from this, if we simplify this, we're going to have j omega out root lc. Let's say this is equation 2. So at lossless transmission line, for a lossless transmission line, you can also have this equation for propagation constant. So comparing equation 1 and equation 2 and taking into consideration the coefficient of J, we are going to have B to be equal to omega root LC. This is also a very important equation under transmission line theory. So in transmission line equations, we have lambda to be equal to 2 pi out of the phase constant. So we can say that 2 pi out of, which is B, the phase constant. But remember that from equation 1 and equation 2, we are able to prove that the phase constant can also be equal to omega root LC. So we can replace this phase constant by omega root LC. In our equations, we also concluded that Z naught was equal to root R plus J omega L out of J plus J omega C. We concluded that this is a characteristic impedance formula. Right, so if you are saying that at a lossless transmission line, or for a lossless transmission line, we are saying that there are no losses. That means no resistance, no G. Right, so it means that all the real parts, that is R and G, are all equal to 0, right? Because there are no attenuations or no losses. So now Z naught is going to be equal to root of J omega L all over J omega C. So we will see that J will cancel J, omega will cancel omega. So Z naught will be equal to L over C. So therefore, Z naught will also be equal to L over C over here. And this is where we are going to end today's session. Thank you for watching.